In this problem, I wanted to use the idea of equivalent circuits and show you how you can use an equivalent circuit to analyze a more complicated circuit. All right, so in this circuit we have several resistors. Let's count them: 1, 2, 3, 4, 5, 6, 7 resistors connected, and a single voltage source. And what I have given here is all the resistances are in ohms. And what I want to do is find the power used by all resistors. All right, so to find the power used by a resistor, I need to know the current through it and or the voltage across it. All right, actually, if I know the current through it, I can get the voltage across it using Ohm's law. All right, and if I know the voltage across it, I can get the current through it using Ohm's law. So I just need these values for every one of the resistors. All right, but it's a reasonably complicated circuit. How would you get started? All right, so here's the path I'm going to do. I'm going to find a series of equivalent circuits. All right, and from one equivalent circuit to the next, I can answer different questions about the overall original circuit. All right, so let's get started. All right, the first equivalent circuit, I'm going to call that EQ1. All right, for equivalent circuit 1. I'm going to draw everything except what I've noticed here is on the right-hand side of the circuit, I have 3 resistors that are all connected in series. All right, so I'm going to draw everything the same, but I'm going to combine those 3 resistors in series. All right, so this would be the original 20, the 60 down here, the 240 stays, the 560 stays. But because these are all in series, I can combine them. And so I'd have 100 plus 120, that's 220 plus 200. This would be 420. Okay, and here is 40 volts. All right, so that's equivalent circuit number 1. All right, I can then do equivalent circuit number 2 and draw this as 40 volts, 20. All right, 240, I'm going to leave the same. I forgot the 60. And what I've noticed is these 2 resistances are in parallel, so I can calculate that. 560 times 420 divided by 560 plus 420. So I enter that into my calculator and I get that that's 240. All right. So this equivalent resistance, I have another 240 here. All right, so that's a second circuit. All right, and then I think you may be able to see what to do next. I notice again a couple of parallel resistors, and so I can come up with a third equivalent circuit. The 40 stays the same, the 20 is the same, but now I combine the 240s into an equivalent parallel combination. 240 times 240 divided by the sum is 120. All right. If you have the same value of resistance and you put it in parallel, it just divides it by 2. It's just a mental shortcut. All right, and I keep forgetting that 60 ohm resistor. All right. So there's a third equivalent circuit, and then finally the fourth one is really fairly obvious, I think. 40 volts. I combine these 3 resistors that I see in circuit number 3 into series, and I would get 120 plus 20 plus 60, which is 200 ohms. All right, so that lets me find this current I that's supplying the equivalent circuit. Okay, so I would be 40 over 200 or 0.2 amps. Awesome. All right, so that's pretty easy. Now what I know is that this value of I translates up in the equivalent circuits. Okay, so when I say translates up, this voltage source has to supply the rest of the circuit over here to the right of this line that I'm just drawing here. It has to supply 0.2 amps. So I can put that in to all my equivalent circuits. I know this is 0.2 amps. All right, so let me highlight that, put that in red. I know these translate up into the equivalent circuits. All right, well, the next thing I can do is I can actually calculate values of power for the 20 ohm resistor and the 60 ohm resistor, because I know 0.2 is going through those. Notice the 120, there's not a 120 in the original circuit. All right, so I'm not interested so much in that, but the original problem said find the power used by all the resistors. I can knock out that calculation for the 20 ohm and the 60 ohm at this point. Okay, so it turns out there's a couple of formulas for power used by resistance. All right, so I'm just going to cover those now, but let's think about it. Power is V times I. All right, but for a resistor we have Ohm's law. So if I solve for V using Ohm's law, V would be I over R, and then I multiply by I, so I get I squared. I'm sorry, that's terrible. V equals I times R. Now we get I squared times R. All right, so that's one formula for power. V times I is another one. And then I can do the same thing. I get V squared over R as the power. So if you know the current or the voltage across a resistor, you can use these two, one of these two formulas to get the power. Okay, so with that being said, let's erase this. All right, what I know for the power for the 20 ohm resistor is 0.2 squared, I squared, times R. Okay, so 0.2 squared times 20, I get 0.8 watts. So there's one of the 7 calculations that I'm trying to make here. I can then get the power in the 60 ohm resistor. I know it's 0.2, the current is 0.2, and you multiply by 60. All right, and so that would be 2.4 watts. And resistors, this is using the passive sign convention. We always use the passive sign convention for resistors, and these would be using power. All right, resistors always use power. Okay, cool. So we got 2 of the 7 done. All right. So at this point, what I'm thinking is, if I could get the voltage, I'm going to change this to red. If I could get the voltage across here, that would be the same as the voltage across here and the same as the voltage across here, because all those are parallel resistances. Okay? So if I could do that, I could calculate the power for the 240 ohm resistor and the power for the 560. All right, so if I know this voltage plus minus V, I would be good for calculating 240 and 560, the power for both those resistors. All right, so I'll look at my equivalent circuits, and I'm thinking, this point, this point where all these connect, in the equivalent circuit, it's here and here, and then here and here. All right, so hopefully you see that. If I could get the voltage across the 120 plus minus V, that value carries backward, if you will, back up through the equivalent circuits. All right, so I do know that because this current is 0.2 times 120, so V would be 24 volts. Okay? All right, so let me go back to the black pen. All right, since I know this is now 24 volts, then I can get P240, because that's 24 squared divided by the resistance. V squared over R gives me power for resistance. So 24 squared divided by 240 gives me 2.4 watts. Okay, I can also get by the same calculation, same type of calculation. I know that V is 24 across the 560, so 24 squared divided by 560. Okay, and I get that to be 1.0286 watts. All right, so how many do I have? I have 1, 2, 3, 4 of the resistor values. I need the other 3. Okay, so I'll go back and I look. Here's the other 3. They're in this branch. All right. Well, I'm looking at this, and I know the voltage across the branch. Okay. I know this is 24 volts from here to here. Let me change it to purple. From here to here, across the branch is 24 volts. All right, and so could I get the current? Well, wouldn't that be this current here, plus minus 24? And then here's the current. Okay, so I, in this case, using just a simple series resistance. If I know this is 24, a rise of 24 is equal to a drop of 24. So this voltage drop is 24 across this resistor. All right, that lets me calculate the current. Okay, so the current is 24 over 420. All right, so the current in that branch is 0.0571 amps. All right, so that lets me do I squared R on the rest of the calculations here. All right, I can get P100, go back to black. Okay, that would be 100 times I squared. All right, I squared was, I'm just going to write it like this, 24 over 420. Okay, P of 120 and 200 are the same type of calculation. Okay, it's V times I squared. I squared is 24 over 420. All right, and that gives me the rest of these calculations. Okay, so this gives you the answers. All right, we now have all the answers. These would all be in watts. I'm not going to actually calculate the values out. You could do that. And then what you have is that if you looked at the power supplied by the 40 amp source, so the power supplied by the 40 amp source is going to be 40 times 0.2. All right, because I know looking at the equivalent circuit, the 40 volt source is producing 0.2 amps. All right, so V times I is 0.2. This is the active sign convention, so this is supplying 8 watts of power. All right, so it should be that when I add up all the power used by the resistors, it balances with the power supplied by the 40 amp source. Okay, so you can practice that and verify that calculation. All right, so in summary, what we did here was we started with a complicated circuit and we came up with 3 equivalent circuits by just looking at series and parallel combinations. From there, we worked our way back up to figure out what voltages and currents we would need to calculate the power associated with any of the resistors in the circuit. All right, so this is a common technique for analyzing circuits. All right, so you'll need to be able to do this on exam 2.